It is the voltage signal. Vertical axis is representing the amplitude of the voltage signal, and horizontal axis is suppose time. Okay. So the signal here, in this case, what we are doing, we are representing the signal as a function of time. And the time is the independent variable, and its amplitude or voltage value V is the dependent variable. So if you see this graph, it is possible to plot the graph of the signal, this voltage signal Vt, as a function of time. Then here it is possible to say what is the value of the signal at a particular time instant. For example, suppose this is 0.1 second. At 0.1 second, what will be the value of Vt? You can measure this. This amount is the value. Similarly, suppose at 0.02 second, this is 0.01 second and this is 0.2 second. Here also it is possible to say what is the value of this. আমি ক্লাস নিয়ে ফোনটা করছি, যাব হ্যাঁ, আজকে আমাকে বাড়িতে যেতে হয়নি। So here 0.1 second, this height is the value or amplitude of the signal, voltage signal, and here at this time instant, this much is the amplitude of the voltage signal. So at each and every instant of time, you can say what is the value of the signal or wave. Okay. And you see, this is, I can say, since this signal depends on only one variable, means time t here in this case. Therefore, it is called one-dimensional signal. Okay. And this signal should be always single-valued signal. Whatever we will discuss in our paper, this course, the signal will be single-valued. Single-valued means for each and every time instant, the signal, each and every value of time instant, for this case I am giving this example. For each and every time instant, it is possible to get only one value of the dependent variable Vt. Single value means corresponding, it is one-to-one mapping. Okay. Corresponding to one value of t, you will get only one value of Vt. Okay. And that's why it is called single valued signal. Now, since it is this V is a function of only one independent variable here, t, therefore it is called one-dimensional signal. If I say what is the example of one-dimensional signal, you can say our speech signal. I am talking here in front of this loudspeaker, a microphone, and the microphone, what the microphone will do, a microphone is actually one kind of transducer which is converting this voice vibration, means voice signal, the vibration, air vibration, into electrical quantity, voltage or current quantity. And this electrical quantity, then it is coming to the computer. First it is converted to, since the computer is a digital device which can deal, which can handle only the discrete data. Therefore, this signal will be first converted into discrete time signal, then it will be converted to digital signal, and this digital signal will be processed by the computer, and it will be transmitted through media. Ultimately, the receiver at the receiver end, again, this digital signal will be converted to discrete time signal, converted to analog signal by using this reverse process. And this analog signal again will be amplified and it will be fed to loudspeaker, and the loudspeaker will reproduce the sound signal and you will be able to listen that. Okay, so this is the architecture, and this is one dimension signal, because whenever I am talking, means due to vibration of vocal cord, the surrounding air is vibrating. And this vibration is obviously a function of time only. Okay. At each and every time instant, the amplitude of sound or vibration, amplitude of the vibration is different. And that is captured by the microphone. Microphone is a converter type of device. Basically, it will capture the sound and it will just generate the electrical corresponding electrical image of the signal sound, electrical image of the sound vibration. Okay. Now, many times, because we are processing the signal in electronic mode, in digital mode, therefore, whatever the signal is available in our nature, if it is not electrical quantity, then I have to make it electrical quantity by using some sensor, by using some transducer type of thing. Sometimes we use sensors also, different types of sensors are available. For example, suppose you want to process the biomedical signal, ECG or EEG or some other types of signals are there. Different types of signals are there in our body, which is to be measured for medical purpose. Okay, so what we do in that case, the signal, biomedical signals are either electrochemical signal, or sometimes it may be vibration also, sometimes it is chemical signals also. Whatever may be the nature of the signal available in our body, that particular signal, first it will be converted to electrical quantity by means of some sensor. So sensor design one part from where we can generate the electrical signal, and that electrical signal then is to be processed by your computer system, because the electrical signal, you have some desire, means you have some interest on some part of the signal, but other signal may be mixed with that particular signal which is desired by you. Then what you have to do, we have to extract the desired part of the signal by removing other part of the signal, or other types of signals, because those signals are interfering your desired signals. And you can do this by using some signal processing system, signal processing method you can apply to do that. For example, I am talking here, okay? So you are listening my voice, and if surrounding me, suppose some machine is running and it is making some sound, the fan is rotating, it is making some sound, then what you will feel at the destination here, when this my voice will reach you, it will reach along with other signals also, other sounds also. Means there's a sound of the machine, sound of the fan, etc. and etc. If someone is talking here, then also that voice is also will reach to you along with my voice. Now your signal processor unit, okay, should be such that it will remove those noise part or those interfering signals. and it will help to extract the signal of your interest. This is the signal processing. And here the system, we will try to design some systems which will perform this kind of processing. Okay. Now, this is what we are saying. This is one-dimensional signal. Now, another type of signal is there. I will classify the signals, different types of signals in the next class, because in this class, I am not starting that part. Okay. Just I am giving a brief concept of what is signal and how can I think that, how can I process that, and what are the means signal we see surrounding us. Another type of signal is there. Suppose signal, I am writing this signal, suppose f, I am writing the signal as fxy. Here fxy means I am writing this fxy is a signal, and we have two variables, x and y. And suppose these two variables are spatial variables. It indicates the distance. Then this fxy is a two-dimensional signal. It is difficult to draw two-dimensional signal here in one-dimensional, here in the plane. But what we can do, we can think that it is possible to write by drawing the axis like this. This is fxy, and this is x, this is y. Then you can plot the signal. Okay. You can plot the signal. For example, a signal is something like this. I am drawing into it. So this signal, a point, it has some x coordinate and y coordinate also. Okay. So x coordinate means the distance of this point from this, suppose this is your z axis, means which is z axis is representing this fxy. Okay, so z is equal to fxy, I am saying that. And here, if you measure the distance of this point from yz plane, that will give you this x value. And if you measure the distance of this point from xz plane, then it will give you the y-axis, y value, means y coordinate value. And the height of this point from xy plane will give you the value of fxy or value of z. So this is your two-dimensional signal. Can you show one example of two-dimensional signal? Yes, it is image. You know, image, photography. Whenever you are capturing some photo, then what you are seeing, all of you know, I think, photo, because you have mobile and you are capturing so many images by using your mobile. Sometimes you are taking your selfie. Okay. So in any photograph, it is a two-dimensional space. And you have some pixel points. The unit of this here, the point of in a point here in the image, it is called actually picture elements. If you think about some grayscale image, means black and white image, the older cameras were black and white. It would produce black and white shades. Okay. And each pixel is represented by a value, for example, 0 to 255. Okay, this is a range of value, and 0 value means black and 255 value means white. And if some point is there which is not exactly black or exactly white, in between this gray, in between these two limits, then I will say that that point is gray point, and gray point will be any other value in between this 0 and 255. So one image consists of a number of pixel points where each point will give you the pixel value or light intensity value. In one sense, I can say light intensity value. And the position of the pixel is actually xy. So you can think that this is x, this is y. So this is x is equal to 1, y is equal to 1. The next pixel is equal to here, x is equal to 2, y is equal to 1. Then next pixel will be x is equal to 3, y is equal to 1, so and so. So in this case, you can say that fxy means xy represents the position of the pixel, and f, it is the intensity value of this point, light intensity value. If you think about colored image, the colored image has 3 channels actually. Corresponding to each pixel, 3 colors are assigned: red, green, and blue. Okay, so corresponding to each pixel, I will say that corresponding to each point in color image, actually 3 8-bit numbers are there. One 8-bit number will represent R, another 8-bit number will represent G, another 8-bit number will represent B, means blue, G means green, R means red. We know that in color theory, actually, any kind of color can be generated by mixing red, green, and blue colors in proper proportion. If you think that the R has maximum value, for example, it has 255 value, and this has 0 value, and this has 0 value, then means green is 0, blue is 0. That means actually this point is representing the red pixel. And if this green pixel is 255, and B also 255, means all pixels are 255, then this point is actually white point. For other values of G and B, other color sets will be represented. Okay, so this is our 2-dimensional image frame. Only one image frame you are taking. Okay. Now this is 2-dimensional. Okay. Similarly, f, x, y, z, this is 3-dimensional, all of you know. Then f, x, y, z, or x, y, t. You can think x, y, t. This is also, what is this? T, suppose t is the time, x, y is the spatial coordinate, t is the time coordinate. That means it is a video signal, 2-dimensional video signal. 2-dimensional video is a 3-dimensional signal actually. Time means actually time t is equal to 1 is one frame, t is equal to 2 is another frame, t is equal to 3 is another frame. So this time represents the frame. Similarly, for 3D video, it will be x, y, z, and t. So this is 4-dimensional signal. So these are the different types of signals. Okay, but in our case, in our paper, I will concentrate on 1-dimensional signal here. But then if another paper is there in your 7th semester, that is image processing, digital image processing, in that paper, actually, this 2-dimensional fxy will be discussed. Okay. So this is 2-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional signals. Now next day I will try to classify different types of signals, and then I will give some examples. Okay. Today it's now 5:12, so let me end the class. Okay. Okay. So whatever. Okay, then let me take this attendance. Okay. No. Since the time is over, therefore it is not permitting to download the attendance now at this moment. So I have to take the attendance within the time, means here from after 4:30 and before 5:10. Okay. Okay, I have taken. Okay, if you have any question, you can ask me. And I want to ask you, if you don't have any class, then it may not be required to take another class. Now, you can give me suggestion. Can I leave now?